Swayam Prabha. Digital India. Educated India.
Hello all, welcome to the lecture 10 of this course. In the previous lecture, we discussed about the power required curves, how the power required minimum is not exactly happening at the same velocity at which thrust required was minimum. Okay, so we just started having analytical discussion on this. So let us continue those. All right. Okay. So now we have power required. Remember, it was thrust required into velocity. And thrust required is exactly equals to the drag into velocity. Okay, remember what was drag? CD equals to D upon QS. That means drag equals to QS CD. Okay, so we write here QS CD into V. So power required we can mention here as QSV. And what is CD? CD is CD naught plus KCL square. Alright, now let me just open this bracket. So this is QS CD naught into V plus QSV into KCL square. We know that Q is equals to half rho V square. Okay, and CL 2W by rho S V square. So let us quickly put these expressions here in the power required. So power required equals to QS CD naught, or you can directly write in the half rho V square. Okay, so this becomes half rho V cube S CD naught plus half rho V square S V into K into CL square. So CL was 2W by rho S V square. So this is whole square. Okay, so power required equals to half rho V cube S CD naught plus 2K W square by rho Vs. So if you solve this, you will get this expression. Okay, remember CD was equals to CD naught plus KCL square. This was induced drag. Or drag due to lift. Right, and this was zero lift drag. Okay, likewise this is known as zero lift power required. Zero lift power required, and this is lift induced power required. Alright, so this is zero lift power required and this is lift induced power required. Now look at the term velocity over here. So at high velocities, this term will actually dominates at high velocity. Alright, but at low velocity, this term will dominate, that is lift induced power required. So dominate at lower velocity. Alright, now let me draw this figure again. That is power required with velocity. Alright, likewise we have drawn for thrust required with velocity. Okay, this is power required with velocity. So at low velocities, so this lift induced power required will be maximum. Alright, so let me start the curve from here. Okay, so this is for lift induced power required. And what about this? At higher velocities, zero lift power required will be maximum, so that will dominate. Okay, then we draw this. Okay, so this is zero lift power required. Okay, and the net effect of this will be this. All right, and this is the net power required. All right, so at this point we are actually getting the velocity at which power required is minimum. All right, and this is the point at which CL power 3 by 2 by CD is maximum. Okay, so this we discussed in the last class as well. So this is power required is minimum at which CL power 3 by 2 by CD is maximum. Okay, that is what I mentioned here. This is the power required minimum, and this is the velocity at which power required is minimum, or velocity at which CL power 3 by 2 by CD is maximum. Okay, so we will follow the similar process here as well. So for minimum power required, we can set this slope equals to 0. That we can actually do the differentiation. All right, so for minimum power required, so dPr by dV equals to 0. All right, so this is our PR. So let me write here dPr by dV equals to, let us do the differentiation of this. We have V cube, so we'll get 3V square. Okay, rest of the terms will remain same. So that is 3 by 2 rho V square S CD naught minus, why minus? Because where we have V in the denominator, so this will be minus V to the power minus V minus 2 minus V to the power minus 2. So you will get minus 2 kW square rho V square S equals to 0. All right, so then let us solve this. So 3 by 2 rho V square S. So 3 by 2 rho V square S CD naught equals to kW square. All right, I can write here half rho V square S, right? Okay, so this becomes 3 by 2 rho V square S CD naught. All right, so this, what is this? W by rho V is half rho V square S. Okay, so CL was W by half rho V square S. So this becomes K CL into W. All right, so now I can write CD naught equals to 2 by 3, I'm just taking to the other side, 2 by 3. So 1 upon rho V square S, 1 upon rho V square S, and here we have K into CL into W. All right, so let me write here 1 by 3. So 1 by 3, and then again let me write here W by 1 by 2 rho V square S, 1 by 3 W by half rho V square S into K into CL. Now this is again CL. Okay, so CD naught we get 1 by 3 K CL square. All right, what was this KCL square? Remember, CD equals to CD naught plus KCL square. This was the induced drag, CDI. Okay, so you can write here CD naught equals to 1 upon 3 CDI. All right, so this is the induced drag coefficient, 1 upon 3 CDI. So now this is the condition for power required minimum. Okay, fine. So what was the condition for thrust required minimum? So for thrust required minimum, the condition was CD naught equals to CDI. Okay, so please do not forget these points. All right, now this is, now for example, if you go back to this figure, if you take this as point 1, So this will be represented by 0.1. Okay, so that is the point for thrust required minimum. All right, now let us continue. That is CD naught equals to 1 by 3 CDI, that is CD naught equals to 1 by 3 KCL square. So I can write here CL easily as 3 CD naught upon K. Alright, so this is the equation for power required minimum. But again, will we tell the pilot that to fly at power required minimum, please fly at square root of 3 CD naught by K? No, right? We need to tell the pilot that please fly at so and so velocity. So what is the velocity which is corresponding to this CL? So V at which power required is minimum. You can write here 2W by rho SCL. Alright. So 2W by rho SCL is 3 CD naught upon K, and this is the square root. So this is the velocity with which the pilot can fly at power required minimum. Okay. Now in the last lecture we also discussed why velocity for power required minimum is less than velocity for thrust required minimum. So the answer you can look at here. So for thrust required minimum, consider this as CL1 equals to, the condition was CD naught upon K, and for power required minimum, condition is 3 CD naught upon K. Okay. So here we have, so this is considering as CL2. Alright. So here CL2 is actually greater than CL1. Okay. So but there is an inverse relation between velocity and the CL. So CL equals to 2W by rho S V square. Okay. So then velocity for 2 will be less than when compared with velocity for 1. Okay. Velocity for 2, the 2 point we considered for power required minimum. So that is why the velocity is low when we consider the power required minimum criteria. Okay. Hence V2 is less than V1, that is velocity for power required minimum is less than velocity for thrust required minimum. Okay. That is why this curve is actually here. This point is actually here. Okay. And there is another note from this figure. Another point you can note from this figure is, let me draw the figure again. So this is power required. This is the velocity. Alright. So now this is power required and this is the velocity. Now if I draw, for example, this is one line which we have here, this is the slope, that is PR by V. Alright. And this slope, what is happening to this slope? At this point, this is the slope, and then at this point, this slope is actually decreasing, and then at this point, your slope is actually become minimum. Okay, and then after that, the slope is again increasing. Alright, so the point here is the slope is actually first of all decreasing, it becomes minimum at this point, and then it again increasing. So what is this slope? Alright. So this is nothing but the slope first of all decreases. Slope PR by V decreases and then becomes minimum. And then again increases. Alright. So this is the tangent point. Okay. This is the tangent point. So this tangent point is actually corresponding to minimum slope. Okay. So tangent point corresponds to minimum slope. Okay, that is minimum value of PR by V. Okay, now if we write in this way, we differentiate with respect to velocity, that is PR by V divided, differentiate with velocity. So this we can write here d by dv. What is PR by V? PR is thrust required into velocity divided by V. So what do we get? This is actually dTr by dV. Alright, so this tangency point corresponds to minimum thrust required. So this tangency point corresponds to minimum thrust required, or let us say L by D maximum. Okay, so even if I go back to this figure, so then this curve, this point is actually representing thrust required minimum, that is velocity for which thrust required is minimum. Okay, now if we, so this point is actually corresponding to velocity at which thrust required is minimum, that is L by D maximum, and this point is actually corresponding to velocity at which power required is minimum, that is CL power 3 by 2 by CD maximum. Alright, now let us find such a point, power required minimum point, by writing this equation in MATLAB. Okay, and let us verify those results. So this was the code, MATLAB code that we had written before. Let me rerun this code for you, where we obtained different figures. Figure 1 was thrust required with velocity, figure 2 is power required with velocity, and figure 3 was the combined result of these two. Alright, now what we have just now derived, the relation for power required minimum. Okay, now let us find here, after the power required, let me write here as velocity at which power required is minimum. Alright, so let me write here V underscore PR minimum. Okay, so that was the expression 2W by rho s square root of 3 CD naught by K to the power 1 by 2. Okay, so I am writing that expression over here, square root of 2 into W by rho into S into square root of K by 3 CD naught. Okay, so now this should indicate velocity at which power required is minimum. Now let me rerun this code again, save it. Alright, now the plots remain same. Let me go to this, velocity at which power required is minimum. So this is the velocity at which power required is minimum, this 64.5875. Okay, so now let us go to the plot at approximately 64.7. Okay, so this is 66,390. Okay, so it is around 390. Okay, go back here. So at 64.58, that is 64.58, we have power required is minimum. That's approximately 64. Okay. Or you can also, okay, alright, so at approximately 64, the power required is 390 kilowatts. All right. So we can even find it out here as well directly in the command prompt. You just have to mention here that is minimum power required, MINPR. Okay. So minimum power required is indeed 390 kilowatts. All right. And now if you want to write the velocity at which this power required is minimum, that also you can do. Okay. You just have to store it in an index. All right. So let me write here. So this is the power required minimum. So you can also even see here. So this is the power required. So 390. So 390. Okay. 390.02. 390.01. Okay, this is around here at the index 20. Fine. Now let me directly write here what is the, let me save the index first. For that command is power required minimum, that is the variable name. Okay, so power required. So let me write here velocity for power required minimum, comma. Let me save the index. So this is equals to minimum of power required. Okay, so that index is actually 20. Okay, that is what we saw. That is why I have shown you over here that at index 20 your power required is 390.0211. That is what it is showing here. Now what is the velocity at this index? So that we can easily find out now, because index is number is saved here as a 20, for example here. Okay, so now if you find here v underscore pr underscore minimum equals to v of the index. Okay, v of index, what is the velocity at this index? So that velocity is will correspond to power required minimum. So this is the velocity at which the power required is minimum, that is 65.0574. Okay, so this is, now see here the analytical expression was velocity for power required minimum is approximately similar. Okay, 65 meters per 6. Okay, 65 meters per second. All right. Now this whatever I mentioned here, it will immediately save in the workspace also. All right. Okay. So now we know how to find the power required minimum and what is the velocity at which power required is minimum. Now we discussed about the thrust available and this maximum velocity. Now let us discuss about power available and its maximum velocity. Okay, so the next topic is power available and maximum velocity. Power available and maximum velocity. Okay, so remember we have written power is force into velocity, thrust required into velocity, which is nothing but W by CL by CD into V. Now again, as we discussed about thrust required, even power required is the characteristic of the aerodynamic design. Okay, it is the characteristic of aerodynamic design and weight. Okay, and weight of the aircraft. But again, power available is a characteristic of the engine, that is power plant. All right, as we discussed for thrust available as well. So power available is a characteristic of the power plant. That is the engine. Now let us talk a little bit about reciprocating engine. So this is the reciprocating engine. Okay. This is the propeller. Okay, so this is the propeller. And this is the shaft. Okay, so that will produce the power available. So how a piston engine generates power? So it generates power by burning fuel in confined cylinders and using this energy to move the pistons. Alright, so it generates power by burning fuel in cylinders, confined cylinders, and using this energy to move the pistons. Alright, which in turn delivers the power to the rotating crankshaft. This one, this which will deliver the power to the rotating crankshaft. Okay, so power delivered to the propeller by the crankshaft is called as shaft brake power. Power delivered to the propeller by the crankshaft is defined as shaft brake power. Okay, remember this. But again, not all power is available to drive the airplane. Some is lost due to the propeller inefficiencies. Some is lost due to the propeller inefficiencies. Okay, so that's why power available is given as some neta efficiency into P. Here neta is nothing but propeller efficiency, and this will always be less than or equals to 1. Okay, neta is always less than or equals to 1. Okay, so power available equals to neta into P. The P is the shaft brake power. Now remember, we talked about the power. These are rated in terms of horsepower. So all reciprocating engines are rated in terms of horsepower or HP. Okay, so 1 horsepower is equals to how many watts? So this is 746 watts. So 1 watt was 1 Newton meters per second. Remember this we discussed. So 746 Newton meters per second. Alright. So please do not forget these units, because most of the time students will commit mistake here while converting from horsepower to watts or to Newton meters per second. Okay, so hence it is common to use this shaft brake power, shaft brake horsepower rather. It is common to use shaft brake horsepower. So you will see power rated in terms of bhp. Okay, so please do not get confused with this term bhp. Alright, now let us draw the curve for power available curve with velocity for both reciprocating as well as jet engines. Alright, so let me first write it for reciprocating engines. This is power available, and this is velocity. So this is almost a constant. Alright, what about jet engines? Remember, there was a linear relationship between thrust and velocity. Okay, so this is power was equals to thrust into velocity. So for jet engine, this is for jet engine. So this relationship will be linear here in this case. Okay, it was constant in the previous case. Okay, thrust was constant with velocity for jet engines. Alright, so here this is power is thrust into velocity. Since thrust is constant, it is varying linearly with velocity. So we get this relation as this curve as a linear relation between the power and the velocity. Alright, so this is for the jet engine. So for propeller driven, power available is essentially constant. With velocity. All right. So for jet engine, for jet aircraft, assuming thrust available is constant, assuming thrust available is constant with velocity. All right. So PA at subsonic speeds, so this varies linearly with velocity. Okay. So now we have discussed both power required and power available curve. Now let us plot these two together. So you will be seeing rather lot of curves between power and velocity as well for both reciprocating and jet engines. So this was the power required, that remains same, and the power available will be almost constant. So this is for reciprocating engine again as well. All right, and the intersection of this will represent your Vmax. All right, what about this for a jet engine? So here we have this linear curve. This is the power available, PA max, and this is the curve. Okay, so this is power required. Okay, now this will be your Vmax. All right, now this is again for a jet engine. This is power with velocity curve. Okay, now again the point remains same, that is the high speed intersection. The high speed intersection of maximum power available and power required curve, defines the maximum velocity for straight and level flight. And these power curves are actually essential for performance analysis of the aircrafts. Okay, so these curves are actually essential for analyzing how the aircraft is performing at similar flight conditions. Okay, now again remember, these curves are all applicable at a particular altitude. Okay, always remember these curves are applicable at particular altitude. Now what happens as the altitude increases? Okay, that is the question that we need to address. That is the altitude effects. On power required and power available curve. Okay, so as I said, the previous curves were applicable for at particular altitude. And what do you think, will the power vary at higher altitude? Obviously the power will vary, right? So power varies as the altitude increases. Power varies as the altitude increases. Now how are these curves, how will these curves vary with altitude? That is what we'll discuss now. Okay, so consider sea level conditions. Consider sea level condition where the V naught is given as 2W by rho naught SCL. Okay, and the power required is given as, remember we have derived this expression power required. Let me show you right here. Yeah, so power required 2W cube by rho S CD square by CL cube. All right, so let me write that expression over here. So 2W cube CD square by rho naught into S into CL cube. See, square root. Now what happens at some altitude? So at some altitude we can mention VALT equals to 2W by rho S CL, okay, and PR at altitude equals to 2W cube CD square upon rho S CL cube. Okay, so the difference here with this, the density. Now as the altitude increases, what happens to the density? This density will reduce, right? As the altitude increases, the density will reduce, and since density will reduce, then the velocity required will be high. Okay, similarly, as high altitude, this density decreases. Okay, so at high altitudes, that means your power requirement will be high. Okay, now assuming this CL remains same, assuming CL remains same, at sea level and altitude. Okay, so then if CL remains same, then obviously CD also will remain same. Then CD also remains same. Okay, since CD equals to CD naught plus KCL square. All right. Now what we'll do is we'll divide these equations by sea level equations. Okay. So what you get, V altitude divided by V naught. Okay. So V altitude by V naught. So what do you get? Rho naught upon rho. Okay. So you can write here V altitude equals to V naught, that is rho naught upon rho. Okay. So if you know this relation rho naught upon rho, what is the density, then you can find approximately the velocity required at that altitude if your CL is same. Similarly, you can find power required for at that altitude equals to power required at sea level into rho naught upon rho. All right. So this is the velocity required, this is the power required. So these equations help us to plot the power required curve at altitude from a given point on the sea level. Okay. So since the density decreases as altitude increases, from these equations we can derive that velocity and power required at higher altitude will increase, maintaining same CL. Okay. So then if this is the point, then what is actually happening to the power required curve? This is power required curve with the velocity, and this is the curve that we have been discussing for over a while now. If this is for sea level, and consider this as point 1, so where we have power required naught and V naught. Okay. Now if we want to consider another altitude, so then at that altitude your power requirement will also be high and your velocity will also be high. So next point will be towards right and towards upwards of this point 1. So say for example, this is point 2. Okay. So at higher altitude, your curve will actually be going in from point number 2. So where we'll be having PRALT, comma VALT. All right. So we were actually trying to find point 2 at different altitude. So by these equations, we just have to multiply by rho naught by rho to get velocity at that altitude, and then find what is the power required corresponding to that velocity. All right. So this was the sea level, and your next curve will actually be going through this point 2. So this is at some altitude. Okay, so this is at some altitude. So this has shifted towards right. So this curve shift upwards and rightwards. Okay, and this is applicable for at some altitude. Alright, so power required curve will actually shift upwards and rightwards for at some altitude. So this was as for power required. What will happen to power available at high altitude? So obviously the power available, what will happen? It will. So let us see what happens if you are not able to guess. So what about power available curves? What about power available curves? So lower air density at altitudes higher than sea level causes reduction in power. Okay. High altitude will have lower density and this will have reduction in power. Reduction in power for both reciprocating and jet engines. Reciprocating piston and jet engines. Alright, now let me draw the curves together. So this was the power required. Let me write here power. So this is for the propeller driven. Okay, so this is the power required and this is the maximum power available. Okay, this is PA max. This is at sea level. This is at PR at sea level. Okay, and this is the power V maximum for sea level. Alright, and now what will happen to the power available? This will actually reduce. So power available will actually come down. Okay, and this is your so this is power available maximum. This is applicable at some altitude and this is power required at some altitude. Okay, so here point to note here is this is now V maximum. Okay, applicable at that altitude. All right, now let me draw for a jet engine. Okay, so now this is power available max at sea level. And this is power required at sea level. Okay, and this is the V max at sea level. So the power available, so now power available will actually be like this, and okay, so this intersection will actually be telling you this is the V max. So these are just rough plots. Okay, the idea is V maximum will actually be lower when for some at altitude when compared with the sea level. All right, now the points to be noted here is note the V max varies with altitude. All right, since the power available reduces, so V max varies with altitude. So the aircraft with which it is flying at the maximum speed at sea level, it will not be possible to fly at the same speed at the higher altitude. Okay, and the second point is again at high enough altitude. Now here we'll have this point at very high altitude. At you can say at high enough altitude. Now the low speed limit. Now the low speed limit is determined by low speed intersection of power available and power required curve. Okay, so instead of V stall. Remember in the previous discussion we said that the low speed intersection of the thrust required and thrust available curve will not tell you the minimum speed with which it can fly, okay, but that was at a lower altitude or at sea level. But if we are talking about high enough altitude, then your low speed limit will be determined by the low speed intersection of power available and power required curve. Okay, let me draw another curve over here to make these things easy. Okay, so let me draw the power required curve over here. All right, and this is the power available. This is maximum power available. Okay, so this is at high altitude. Please note this is at high altitude. Okay, and this is power required. So earlier your V stall was somewhere around here. Okay, V stall was somewhere around here, but now here we have this low speed intersection. This low speed intersection will define your V minimum. Okay, so this is the point worth noting over here. So hence stall speed cannot be achieved and stall speed cannot be achieved in steady level flight. Okay, so this point is actually worth noting. And the final last point I'd like to mention here is the power available altitude curve for jet engines. Okay, so for jet engines, this was for jet engines. Okay, power available curve for the jet engine. The altitude effect on the thrust here, the altitude effect on thrust is assumed to be proportional to air density. Okay, specifically for jet engines, the altitude on thrust is supposed to be assumed to be proportional to air density. For example, thrust available for altitude, this is for rho altitude, and this is for divided by thrust available at sea level. This is density at sea level. So you have thrust available at altitude equals to thrust available at sea level. Here we have rho altitude upon rho naught. Okay, similarly for power available at altitude equals to power available at sea level into rho altitude upon rho naught. All right. Okay, so these are the 3 points that needed discussion. The first is the velocity, maximum velocity varies with the altitude. At high enough altitude, low speed limit is determined by the lower speed intersection of power available and power required curve, that is instead of V stall. So this V stall is actually cannot be achieved. And the third point was the altitude effect on the thrust is assumed to be proportional to the air density. Okay, so thrust available at altitude is given by this relation. Okay, so if we know this relation rho by rho naught, then we already also know what is the thrust available at sea level, what is the power available at sea level, you can find out approximately what will be the thrust required and power required at that altitude. Okay, now let us take the same example that we have been considering as of now. We will consider the same jet aircraft. So now we will find what is the maximum velocity at 10 kilometers altitude. What is the velocity at 10 kilometers altitude by plotting power required and power available curve. Okay, now assume density at 10 kilometers is given to you, that is 0.4135 kilogram per meter cube. Alright, now let us quickly switch to MATLAB. Now let us plot it in MATLAB and write the code. First of all, the power required, how it varies with at different altitude. Now this was the code that we had earlier written, that is power required curve. I have copied till here and named this file as altitude. So now we will be finding density. I will be writing separately density. So rho SL, that is density at sea level, is 1.225. All right, let me write here at sea level. Okay, then rho underscore 10 kilometers, rho underscore 10 equals to 0.4135. So this is at 10 kilometers. This is at 10 kilometers. Now we will be finding what is the power required at sea level. Power required at sea level. Okay, so this expression that will be same, CL underscore sea level. I am just writing here sea level, that is 2W by rho V square S. So let me write from here. W by rho V square S. So this is rho underscore SL. Rest everything remains same. Okay, and next CD underscore SL. CD underscore SL equals to CD naught plus KCL square plus K into CL square, that is CL underscore SL dot square. All right, next thrust required at sea level, this is equals to W dot into CDSL by CLSL. Okay, now we have thrust required at sea level. You can immediately find power required at sea level equals to thrust required into velocity divided by 746. Okay, thrust required underscore sea level dot into V underscore sea level divided by 746. Okay, so now what you will get now? You will get the power required in horsepower. Okay, power in horsepower. All right, now we got the power required. Now let us focus our attention on power required at 10 kilometers. Power required at 10 kilometers. So PR underscore 10, we can directly use this relation PR underscore SL that we have just now discussed into square root of rho SL by rho 10. Okay, rho SL by rho 10. Okay, fine. Now we'll go to the thrust available. Okay, so thrust available at sea level is that we have already mentioned. So 16242.5 into 2. Okay, I'm writing again here. Then what will happen to the thrust available at 10? Okay, so that is TA underscore SL into rho 10 upon rho SL. All right, into rho 10 upon rho SL. Okay, this is the thrust available. Similarly, power available underscore SL equals to thrust available sea level into velocity at sea level. Okay, this again we have to divide it by 746. Now what we are getting? Power available in horsepower at sea level. Power available in horsepower, okay, at sea level. Now similarly, power available at 10 kilometers, can write here thrust available at 10 kilometers, into velocity at 10 kilometers. Okay, velocity at 10 kilometers. Velocity at 10 kilometers. So this you can mention here as velocity at 10 kilometers divided by 746. Okay. Okay, so let me just save this code. We just left with the plotting. Okay, so now in the next class, I'll show you how the power available and power required curves are different at sea level as well as at 10 kilometers altitude. All right, thank you.